Welcome back to the Cosmos Corner, the space where we unlock the mysteries of the universe together. Today, we're diving into a groundbreaking discovery by the James Webb Space Telescope, JWST, that takes us further back than ever before, right to the edges of the Big Bang. If you're fascinated by how our universe came into being and what secrets lie beyond the observable, make sure to hit that subscribe button and ring the bell for more space revelations. The universe expanded impressively, marking the onset of a dynamic and illustrious era. As time marched on, this expansion continued, but the pace gradually slowed, transforming into the vast cosmos we observe today. This concept forms the basis of the inflationary theory of the Big Bang, the most widely accepted and recognized explanation of the universe's origins. However, some physicists believe this prevailing theory doesn't fully capture the complexity of our universe. They propose an alternative view: the universe existed even before this event, stretching endlessly into both the past and the future. According to this perspective, the universe was contracting before the Big Bang. Contrary to the common imagery of an explosive beginning, these theorists suggest that the Big Bang was more of a bounce, a pivotal moment when the contracting universe reversed direction and began expanding anew. This hypothesis suggests that the universe might continue to expand indefinitely, only to contract again in the distant future, leading to another bounce. According to some physicists, this cyclical process could potentially go on forever. What's really happening with the universe? Traditionally, scientists have embraced the idea that everything started with the Big Bang. However, renowned physicist Brian Cox has raised questions about this concept, challenging the notion that something could emerge from nothing. Adding fuel to this debate, recent startling discoveries by the James Webb Telescope contradict the prevailing idea that the Big Bang marks the beginning of the universe. These revelations prompt us to reconsider: if the Big Bang wasn't the start, what was? Could the universe have begun with some kind of cosmic bounce, or perhaps something entirely different? The notion that the universe had a definitive beginning, a night without a prior morning, was first proposed by Georges Lemaitre in 1927. Although this concept is appealing, it suggests that the universe's inception might be unrelated to the familiar Big Bang that we associate with the birth of our cosmos. Despite the growing evidence, a significant yet minority group of experts steadfastly believe that the Big Bang still represents the commencement of our universe. This ongoing debate continues to challenge our understanding of cosmic origins, pushing the boundaries of what we thought we knew. At the very beginning, the genesis of everything was far more complex than the simple notion of the Big Bang being the birth of life as we know it. In fact, there is a substantial body of evidence pointing to a different origin for our universe, an origin not reliant on cataclysmic events or extreme temperatures. Instead, what defines our universe is an inflationary period that predates the Big Bang. This inflationary era set the stage for what would eventually lead to the Big Bang, which is better understood as the culmination of a series of cosmic events. During this pre-Bang evolution, the universe was essentially a vast expanse of nothingness. No particles, no photons, just empty space filled with immense energy distributed evenly throughout. Over time, this energy transformed as space itself expanded rapidly and relentlessly. As the universe grew, this expansion eased, allowing for significant large-scale changes and the introduction of subtle micro-variations. These layers of complexity, scaling across different magnitudes, are crucial to understanding cosmological expansion. This process unfolded not by design, but through a series of natural, albeit unpredictable events. Imagine living in a universe that's still growing. You might find yourself near areas where this expansion has just ceased, or you might experience a sudden, dramatic increase in the space between you and these regions. This scenario lets you explore the very onset of a cosmic event, moments before these places fade from sight, swallowed by the universe's relentless growth. At the beginning of such an event, The space involved might be no larger than a human-sized hamster ball, though it's likely much larger. The energy stored in this region rapidly transforms into radiation. This transition happens almost instantaneously, as the energy bound up in the fabric of space itself converts into particles and photons. The temperature, almost at absolute zero initially, soars to about 20 Kelvin in the same brief moment due to the enormous surge of energy released. As this energy shifts, everything begins moving nearly at the speed of light. All particles, whether they have mass or not, behave like radiation carrying immense power. This pivotal transformation, known as heating, signals the end of expansion and ushers in a new phase of the universe. This intense and rapid change outlines the fascinating dynamics at play in the evolving cosmos. As the saga of the Big Bang unfolds and evolution marches on, you'll observe a profound shift from any previous state of the universe. As the latest phase of the Big Bang kicks off, the expansion of the universe noticeably slows following the initial burst of growth in an inflationary universe. In this dynamically changing cosmos, regions that once expanded quickly begin to stretch more moderately. As the expansion halts and the new phase of the Big Bang ignites, distant areas start to recede more slowly. Over time, parts of the universe where expansion stops will experience a decline in the rate of expansion, while surrounding regions continue to expand without interruption. In this universe under expansion, any given distance is expected to double after a certain period. When that same amount of time passes again, the distance doubles yet again. However, once the Big Bang commences, this pattern alters, and the expanding universe begins to slow down after the initial moment of change. Before the Big Bang, you might encounter the tapering off of expansion in nearby areas. These regions where expansion ceases will gradually fill with matter, antimatter, and radiation, expanding more slowly than those areas still actively stretching out into the cosmos. As you find yourself within the burgeoning zones of the universe, you're essentially a local in a vast expanse of space-time. Here, regions pulsing with warm, immense bursts of energy drift apart from quieter areas where expansion persists. In this classical inflationary model, these regions recede from each other so quickly, they soon disappear from view, leading to varying rates of expansion across the cosmos. In this scenario, the likelihood of these distinctly heated universes ever interacting becomes minimal. The area we inhabit turns out to be extraordinarily fortunate. Here, expansion ceases, and the energy that once saturated space itself transforms into a warm, dense, and nearly uniform sea of particles. These particles exhibit only minor deviations from uniformity, except for the cosmic quantum fluctuations that stretched out during the universe's expansion phase. These quantum fluctuations play a critical role. The positive fluctuations lead to initially over dense regions, which are the embryonic forms of massive galactic structures. Conversely, the negative energy fluctuations convert into initially underdense regions, setting the stage for cosmic voids. Today, these initial density fluctuations, once vivid during the universe's expansion, serve as the seeds for the vast cosmic structures we observe, though their earliest forms are beyond our current sight. The universe initially underwent a tumultuous period known as the Hot Big Bang, yet from that era, no tangible marks remain accessible to us today. The first clear imprint we can study appears from about 380,000 years later, after undergoing dramatic transformations. Although we can look back and extrapolate the initial density fluctuations to piece together the story of cosmic evolution, the temperature variations etched into the cosmic microwave background, CMB, offer evidence of how the Big Bang unfolded. Yet, there are discrepancies between the CMB observations and our current model of cosmology, suggesting we're missing some key pieces of the puzzle. One intriguing inconsistency lies in how the universe behaves on particularly large scales. It's not acting as expected. The light from the CMB is being lensed or bent by the matter between us and the CMB. This lensing acts like a cosmic magnifying glass, altering and amplifying the light as it travels to us. The extent of this lensing often doesn't align with our contemporary cosmological models, presenting a significant challenge for astronomers. Addressing these discrepancies is crucial for advancing our understanding of the universe's most fundamental forces and structures. In the cosmic microwave background, CMB, sky, observations at the equator reveal differing average temperatures, challenging the expectation of uniformity at the universe's earliest stages. This inconsistency hints at a potential flaw in the conventional understanding that the universe began uniformly. Furthermore, the value of the Hubble constant, which measures the universe's expansion rate, varies depending on whether it's derived from the CMB or observations of nearby stars. Together, these anomalies indicate that our current interpretation of the universe might be missing something crucial. One innovative solution is proposed by loop quantum cosmology, which stems from loop quantum gravity. In this framework, gravity itself is thought to consist of discrete units called quanta that weave the fabric of existence. Instead, the universe would never reach such an extreme state near the Big Bang. In this scenario, as the universe was incredibly compact, quantum corrections played a significant role, exerting tremendous pressures and dictating the dynamics of the cosmos's early moments. Instead of emerging from a singularity, our universe may have originated from a prior universe that contracted before expanding again, much like a phoenix rising from its ashes. This concept of a cosmic bounce, while not entirely new, is given robust mathematical backing through loop quantum cosmology. Intriguingly, this idea also finds echoes in Hindu cosmology, adding an intriguing layer of historical resonance to the theory. If loop quantum cosmology holds true, the early universe would have been characterized by moderate energy and density levels. These conditions could subtly alter the cosmic microwave background, CMB, manifesting as minor temperature variations across the sky. These variations, measured through the power spectrum, could provide pivotal evidence of the universe's beginnings and support the possibility of a cosmic bounce. Loop quantum cosmology presents a fascinating alternative to the traditional Big Bang model, potentially resolving many long-standing inconsistencies in cosmology and offering insights into the origins of the universe. It also provides a promising explanation for the third anomaly, introducing a novel perspective on the underlying mechanics of our cosmos. The noticeable temperature differences across the equator of the cosmic microwave background, CMB, sky present a puzzle that loop quantum cosmology may help solve. This theory addresses key anomalies observed in the CMB, such as the unexpected uniformity on large scales and the puzzling lensing effects that alter the path of light traveling through the cosmos. According to Dr. Venet Goand of the National Institute of Advanced Research, the idea that these inconsistencies are not mere measurement errors but stem from early quantum gravity effects is gaining traction. The concept of the universe beginning with a vast bounce rather than a singular explosion has been floated before, but it demands rigorous empirical validation. This monumental task represents a significant challenge as our observations are limited to specific parts of the universe, complicating our understanding. Dr. Dwayne Johnson, a co-author of a pivotal study and a professor at Penn State University, underscores the difficulties in validating such theories due to their immense scope. However, the introduction of novel theories like loop quantum cosmology holds promise for addressing specific cosmological quandaries. Despite these advancements, the overarching question remains: did the universe have a beginning at all? Advocates of a perpetual universe continue to debate this fundamental aspect of our cosmic history, keeping the mystery of our origins tantalizingly alive. Advocates of a universe with a definitive beginning assert its necessity, but this raises intricate questions about the nature of the event that initiated everything. Cyclic cosmology offers an alternative, proposing an eternal universe that experiences continuous astronomical cycles. However, physicist William Kenny from the University at Buffalo has identified a critical flaw in this concept. Entropy. Entropy, a measure of disorder in a system, is predicted to increase with each cosmic cycle, leading to an inevitable depletion of usable energy. This entropy dilemma suggests a starting event, like the Big Bang, contradicting the notion of a perpetually cycling universe. While newer cyclic models try to address this issue by incorporating long periods between cycles to dissipate entropy, Kenny's findings argue that the universe likely had a distinct origin. His research underscores the ongoing debate surrounding cyclic universes and stimulates further exploration into their viability. Critics of cyclic cosmology have yet to fully counter these entropy-related challenges. The scientific discourse continues to evolve, driven by the quest to uncover the origins and ultimate fate of the universe. Quantum cosmology and updated cyclic models remain at the forefront of this dynamic field, pushing the boundaries of our understanding of the cosmos. As cosmologists like Nelson dos Santos from the Brazilian National Institute for Space Studies delve into the intricacies of bouncing and cyclic models, they confront various anomalies. While loop quantum cosmology offers intriguing solutions to discrepancies in the cosmic microwave background, CMB, its practical utility remains under scrutiny. Nevertheless, dos Santos champions the concept of a cyclic universe. Given the immense lifespan of the cosmos, he argues that a perpetually existing cyclic universe seems more plausible than one sparked at a singular moment. As a dedicated researcher, dos Santos remains committed to exploring all possibilities, acknowledging that the origin of our universe is still shrouded in mystery. Meanwhile, discussions about the ultimate fate of the universe are gaining intensity. The future of the cosmos hinges on its current composition, which includes mysterious dark energy and matter. Determining its destiny involves critical scenarios, either endless expansion or eventual contraction. In one scenario, the universe could expand indefinitely, leading stars to eventually exhaust their fuel and leave behind cosmic remnants like white dwarfs and black holes. Yet, the ultimate fate of the universe also depends significantly on the nature of dark energy and how it influences cosmic dynamics. If dark energy, a mysterious force driving the universe's expansion, remains constant, we're headed towards a cold, dark freeze. In this scenario, matter drifts farther apart and entropy increases, leading to a vast, empty cosmos. Conversely, if there's enough matter, the universe's expansion could slow and eventually reverse, contracting back upon itself. This could set the stage for a cyclic universe model, where the cosmos undergoes endless cycles of expansion and contraction, never reaching infinite density or having a definite beginning. Each cycle heralds a new epoch, offering a more hopeful alternative to a desolate cosmic end. The significance of our existence and the fleeting nature of time itself. Before we delve into the discovery, let's understand our stargazer, the James Webb Space Telescope. Launched in December 2021, JWST is the most powerful space telescope ever built, designed to peer back over 13.5 billion years. It observes the universe through infrared technology, which allows it to see through cosmic dust and gas, revealing the never-before-seen phases of the cosmos. Recently, the JWST provided data that might indicate events preceding the Big Bang. Scientists have found peculiar light signals that don't align with the current models of the universe's early moments. These signals suggest the presence of electromagnetic radiation from before the Big Bang, potentially rewriting our understanding of cosmic origins. What does this mean for science? If validated, this discovery challenges the conventional model of the universe's inception, dominated by the Big Bang theory. It introduces the possibility of a pre-existing era or conditions that led to the Big Bang. This could open up new theories about a cyclical universe or even multiple universes existing in a larger multiverse. The scientific community has reacted with a mix of excitement and skepticism. Validating these findings involves extensive peer review and additional data collection. Researchers are now designing new experiments and observations to confirm or refute this revolutionary hypothesis, ensuring that any conclusion drawn is solid and reliable. This is just the beginning. The James Webb Space Telescope will continue to observe these signals and other celestial phenomena. Each piece of data helps construct a more detailed map of the universe's history and structure. Future missions and technological advancements will likely build on JWST's findings, pushing the boundaries of what we know about our universe. The signals observed by JWST might suggest that some form of energy or matter existed before the Big Bang. This segment delves into the theories about what these signals could be, ranging from quantum fluctuations to unknown cosmic phenomena that defy our current understanding of physics. Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q&A sessions with experts. Your membership will grant you the chance to participate in live Q&A sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos, and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together, we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comments.